Hi everyone. So I'll be talking about our work graph streaming lower bounds for parameter estimation and property testing via a streaming XOR lemma. And this is joint work with Sapir Asadi at Rutgers. In this work, we study the graph streaming model, where our input is an n-node graph and its edges arrive one after the other in the stream. On the stream, we want to solve graph problems in one or a few passes while only using a limited amount of memory. So there are two main areas of research in graph streaming. The first being the semi-streaming regime, where our algorithms are allowed n polylog in space, and the goal is to find solutions to problems on this graph. So for example, we want to find a matching of the graph or find a spanner of the graph. And since writing down these solutions might itself take order n space, it's not really possible to hope for sublinear in n space algorithms for these problems. But if we were to only ask for estimating the sizes of these solutions, maybe there is some hope. And that's where the sublinear space regime comes in. Here, our goal is to estimate the graph parameters, and we allow our algorithms only polylog in space. So an example of a problem here would be to estimate the size of the maximum of the graph, or to estimate the size of the maximum matching of the graph. And in this work, we study the sublinear space regime, and the goal is to prove space-pass trade-offs. So we'll work with what are called cycle counting problems. And here the goal is to distinguish between a graph which consists of many short cycles from one which consists of a few long cycles. So this class of problems was introduced by Verby and Yu, and it captures the sense of many important problems streaming. So for example, when the cycle lengths are odd, it captures max curve. And the reason is that if we consider an odd cycle, any cut of the graph must leave out at least one edge from the short cycle. So when the graph consists of many short cycles, the maxed value will be small. On the other hand, when the graph consists of a few long cycles, then a maxer would not have to leave out many edges in the graph. So the maxer value would be large. So here proving a lower bound on cycle counting when the cycle lengths are odd would prove a lower bound and estimating the size of the maximum of the graph. And this is true not just for max curve, it is true for many important problems that proving lower bounds on cycle counting in the streaming setting would imply lower bounds on these problems also in the streaming setting. So this class, Verwin and you consider a specific cycle counting problem, which they call the gap cycle counting problem. And here for fixed parameter k, which is typically a constant, we wish to distinguish between a disjoint union of k cycles from a disjoint union of 2k cycles. So in this example here, k is 4, and the graph on the left consists of many 4 cycles, and the graph on the right consists of a few 8 cycles. And the goal is to distinguish between these two cases. So Verby and you proved a lower bound for single pass streaming algorithms for gap cycle counting, where they showed that any such algorithm requires at least n to the 1 minus of 1 over k space. And the proof is by a new communication complexity problem called the Boolean hidden hypermatching problem. And this was itself based on prior work in quantum communication complexity. And it turns out that their lower bound is tight. If we just sample n to the 1 minus of 1 over k edges and just check if they form a k cycle or not, then this algorithm would be correct with constant probability. Uh, so so the lower bound of Verby and U is tight. So subsequently, the lower bound on gap cycle counting and BHH was used to prove lower bounds on many different problems. And some of these are mentioned here, but all of these were for single pass streaming algorithms. But now the question is, what about multi-pass algorithms that solve gap cycle counting? So if we allow our algorithms k over 2 passes, then this problem can be solved in log n space. What we do is we just start from one of the vertices in this graph and construct a BFS tree by incrementing its depth by 1 in every pass. And at the end of k over 2 passes, we just check if this BFS tree intersects with itself. But if we only allow our algorithm square root k passes, then this becomes then we only have a near linear space algorithm. And what it does is it samples vertices which are at distance 2 square root k from each other. And we would construct BFS trees now which are rooted at all of these vertices. In every pass, we increment the depth of these BFS trees by 1. At the end of square root k passes, we just check if the union of these square root k depth BFS trees contains a k cycle or not. So it's clear that allowing more passes makes this problem easier. We were able to go from a near linear space algorithm to a one which only uses logarithmic space if we allowed k over 2 passes instead of square root k. But now the question is, uh, how much easier does it make the gap? These passes really make this gap cycle counting problem? And specifically, we wish to answer the following questions. So we want to know how much space is needed to solve this problem in constant number of passes, even in 2 passes. And for a fixed space bound, say polylogarithmic space, we wish to know how many passes are really needed to solve this problem. So it turns out that all lower bounds for all problems in this line of work, including for important ones like MaxCut, were for single pass algorithms. And the key reason for this is that BHH is easy in 2 passes. So only last year, Asadi, Kol, Saxena, and you proved the first multi-pass streaming lower bound. And they showed that any p-pass streaming algorithm for gap cycle counting requires n to the 1 minus O of 1 over k to the 1 over p space. As a corollary, they obtained that omega of log k passes are needed to solve gap cycle counting in polylogarithmic space. So the lower bound even holds for distinguishing a disjoint union of k cycles from a single Hamiltonian cycle. And subsequently, they were able to prove multi-pass lower bound for many parameter estimation and property testing problems. But none of these bounds were tight. And the reason for this is that their bound for gap cycle counting is itself not tight. So for example, when we consider polylogarithmic space algorithms for gap cycle counting, the lower bound was omega of log k passes, while the upper bound which we just saw was k over 2 passes. So that's where we come in, and we prove optimal lower bounds for a version of gap cycle counting problem, which we call the noisy gap cycle counting problem. And here, what we do is we allow instances of gap cycle counting to also contain the short disjoint paths, which we call as noise. And now the goal would be to distinguish a disjoint union of k cycles and its noise from a disjoint union of 2k cycles and noise. And this noise is precisely theta of n over k vertex disjoint paths of length exactly k minus 1. So it would be good to have this picture in mind. Again, here k is 4. So the formal definition of this noisy gap cycle counting is the following. So for a graph which is on 60k vertices, an instance of noisy gap cycle counting either consists of 2t vertex disjoint k cycles and noise, or t vertex disjoint 2k cycles and noise. And in both cases, the noise is 4t vertex disjoint paths of length exactly k minus 1. So, so the addition of these extra noisy paths does not change the complexity of the gap cycle counting problem by much, and we'll see this soon. And nor does it change the nature of the reductions from the gap cycle counting problem. So this is the main lower bound that we prove. So we show that any p-pass streaming algorithm for noisy gap cycle counting requires omega of n over k to the 1 minus O of p over k space with some 1 over poly p factors. And as a corollary, we obtain that omega of k passes are needed to solve noisy gap cycle counting in n to the little of 1 space. So I must mention that our lower bound is asymptotically optimal for all ranges of passes p. And as a consequence in streaming, we show that any n to the little of 1 space streaming algorithm that computes a 1 plus epsilon approximation to many important parameter estimation and property testing problems. For example, max cut, matrix rank, or property testing connectivity bipartiteness requires omega of 1 over epsilon passes. And the previous lower bound for all of these problems was omega of log of 1 over epsilon passes, which was proved in AKSY20. So one thing I should mention about our lower bound is that the hard instances of these hard instances for all of these problems are extremely simple graphs. They are bounded degree and planar graphs, and our lower bound holds even for such simple graphs. So in the rest of the talk, I'll go over the high level ideas that we use in our proofs. And for that, we require some definitions. So here we have what is called a layered graph. It's a graph which consists of d plus 1 layers, so that every layer consists of exactly w many vertices. And now we have perfect matchings between layers. So on a layered graph, we consider what is called a pointer chasing problem. So here we are given a start vertex S in the first layer and an unique partition of the final layer into sets X and Y. So now the goal is to distinguish between between two cases. One is when the vertex reachable from S is in X in the final layer, and the other is when the vertex reachable from S is in Y in the final layer. And this is an instance of pointer chasing where the vertex reachable from S is in X in the final layer. So this problem has been used to prove space path trade-offs in many work in streaming. So these are just a couple of references, but now the question is whether pointer chasing really captures the problem which we are trying to prove a lower bound on. So it turns out that pointer chasing captures the following idea. If we start at one of the vertices in the graph and follow the cycle starting from that vertex, then in k plus 1 steps we can decide the k cycle or 2k cycle problem. But our problem is different than pointer chasing. The reason being that now our graphs consist of many k cycles or many 2k cycles, and an algorithm might do something that is much more complicated than just following one of these cycles, especially in multiple passes. So we need a problem that captures this noisy gap cycle counting much better than what pointer chasing does. So that's where we define our correlated pointer chasing problem. So here, now instead of being given just one vertex in the start layer, we are given a bunch of vertices in the start layer, which are in the set S. But now the problem comes with some promise. The promise is that all vertices in S reach vertices in X in the final layer, or they reach Y in the final layer. And the goal is again to distinguish between these two cases. So for example, this is an instance of correlated pointer chasing where all vertices in S reach vertices in X in the final layer. And here they reach Y in the final layer. So I'll talk shortly about why correlated pointer chasing captures noisy gap cycle counting better than what pointer chasing does. But let me show the plan for proving noisy gap cycle counting. And as you have noticed, the first step itself is showing that correlated pointer chasing captures noisy gap cycle counting. And this is done by this gadget reduction, where we take a correlated pointer chasing instance, connect it using these, make 4 identical copies of it, and connect it using these red edges, such that in one case we have many k cycles and noise, In the other case, we have a few 2K cycles and noise. So using the gadget reduction, now we can say that it suffices to prove a lower bound on correlated pointer chasing, and it would prove a lower bound with the same probability on noisy gap cycle counting. So step one is complete. Let's move on to step two. So here we perform what is called a decorrelation step, and we show that correlated pointer chasing itself reduces from a version of pointer chasing which requires a low probability of success. So this is done by a hybrid argument, and we show that it suffices to prove a half plus 1 over constant times W lower bound for pointer chasing. And as you may have noticed, this is an extremely low probability of success that we now require. So existing techniques for proving lower bounds on pointer chaining will not work. And that is why we require this step three, which is our main step. So here we show that low probability version of pointer chasing that we now require itself reduces from a standard version of standard version lower bound on pointer chasing, and we can use a hardness amplification result that we prove called the streaming lemma to on the standard regime pointer chasing lower bound to prove the lower bound that we require in step two. So let me quickly go over the motivation for step three. And as I said before, now the probability of success that we require for our pointers using lower bound is extremely low, but and we cannot directly prove it. But the hope is that maybe we can perform some kind of a hardness amplification where we take a lower bound on pointers using which we can prove and boost its probability of success. So in the context of pointer chasing, what we want to do is we want to take a large pointer chasing instance, break it up into smaller pointer chasing instances, prove lower bounds on these smaller pointer chasing instances, and put them together using some kind of a hardness amplification to prove a lower bound on the large pointer chasing instance that we started out with. So this is the motivation for our step three. And now we define what is called an XOR product of layered graphs. So what it does is it takes a large pointer chasing instance and breaks it up into an XOR of smaller pointer chasing instances. So once we do that, now our job becomes that we want to use this XOR product and a lower bound on these smaller pointer chasing instances to prove a lower bound on these XOR of pointer chasing of these instances. So let's before we get to the lower bound, let's first talk about the algorithms that can solve this XOR of pointer chasing problems. So let's assume that we have a p-pass algorithm that solves these that can solve these smaller pointer chasing instances, and our goal is to use that algorithm to compute this XOR of pointer chasing problem. And one way to do it is to just use that algorithm on each of these smaller pointer chasing instances and just output the XOR of the answers. So so it turns out that this algorithm would be correct would correctly solve this XOR of pointer chasing problem with probability half times 1 plus 2 to the delta to the L, 2 delta to the L. And the reason for this is that the bias of X, the XOR of L independent coins behaves this way. So, but now we are interested in a lower bound. So we prove what is called an XOR lemma, which essentially says that any p-pass algorithm that tries to compute this XOR of pointer chasing problem does not perform better than this naive way of computing the XOR of pointer chasing that we just mentioned. And in fact, we prove an XOR lemma for any function f, not just pointer chasing, and we just apply it to pointer chasing. So let me now mention our XOR lemma, our streaming XOR lemma. So it says that if we have any p-pass space streaming algorithm, if we have a function f such that any p-pass space streaming algorithm that can compute it over a distribution mu and succeed with probability at most half plus delta, then any p-pass space streaming algorithm that computes the XOR of L independent copies of F, which are independently drawn and given this concatenated stream, would succeed with probability at most half times 1 plus 2 delta to the L. So basically our XOR lemma is saying that any p-pass space algorithm that computes this XOR of L independent copies of F does not perform better than this naive algorithm that approaches these independently drawn copies independently. So let me mention a few quick things about this XOR lemma. The first is that our XOR lemma is as strong as possible. Then the reason being that space is a reusable resource. And this is similar in spirit to Yao's classical XOR lemma, in that it's a hardness result of independent interest. So, and the reason for this is that we were able to use the lower bound on F over a distribution mu as a black box. So let me now go over the proof of the overview of the proof of this XOR lemma. It is proved by first constructing this this non-standard L player communication game, where we have players that get independently drawn input stream, and they communicate via Blackboard. And the computational power that we now allow them is that they can run streaming algorithms. And at the end of the protocols in this game, of a protocol in this game, they have to compute the XOR of F on their input streams. So our XOR lemma is proved in this communication game, and it is done in the following ways. The first thing that we show is that any streaming algorithm that computes the XOR of F implies a existence of a communication protocol in this game. So now we can focus on all protocols that compute the XOR of F in this game. And then we show that no protocol that solves for the XOR of F in this game can estimate the bias of F on any player's input better than if it were to be solved for independently. The next thing we show is that the player's inputs, which were independent before the start of the game, they stay independent even after communication in this game. So the best thing the players could do was to just solve for F on each player's inputs independently and then output the XOR. So, and as I mentioned before, the first thing we prove is that our streaming algorithm is a protocol in this game. So any streaming algorithm must also approach these independent subproblems independently. And that concludes the proof of our XOR lemma. So now we apply this XOR lemma to our pointer chasing problem. And we show that it suffices to prove a lower bound with a much weaker probability of success. And that's what we do in step 4. So now we go and prove a standard regime lower bound for pointer chasing. And this is done by following standard approaches, but it is slightly different because now we have to deal with random matchings between consecutive layers rather than random functions which people have already considered. So now substituting these parameters in this weak pointer chasing lower bound, we recover our main result, which says that any p-pass streaming algorithm for noisy gap cycle counting requires omega of n over k to the 1 minus O of p over k passes space, with some 1 over poly p factors. And concluding my talk, so we defined a relaxation of the gap cycle counting problem, which we call a noisy gap cycle counting problem, where our graph is either a collection of vertex disjoint k cycles or 2k cycles and some noise. And the noise in both cases is theta of n over k vertex disjoint k minus 1 paths. And we prove asymptotically optimal lower bounds on it. As an ingredient of our main lower bound, we prove a streaming XOR lemma, which says that if we have any p plus s space algorithm, we have a function such that if any p plus s space streaming algorithm can only solve this problem on a distribution with probability half plus delta, then any p plus s space streaming algorithm can only solve the XOR of L independent copies of f with probability at most half times 1 plus 2 delta to the L on this concatenated stream. And as a consequence of our main lower bound, we show that finding a 1 plus epsilon approximation to many important problems in graph streaming, for example, to the size of a max cut or maximum matching, or property testing bipartiteness or connectivity, either takes n to the omega of one space or omega of 1 over epsilon passive. And many of these lower bounds are optimal. And yeah, thanks for coming.